Hello, everyone. I'm really excited to be here. Finally, have some time to actually talk about the things that we've done in the past months. Yeah, as mentioned, my name is Dig or Friedel, whatever you like, and I work for Protocol Labs. Here with me are Sean and Kelly from Supernational, who have been collaborating with us for quite a while now, but especially this past month to push the crypto and Filecoin to the next level and to make Filecoin a really fast network. So without further ado, Sean, if you want to say some words about you, Kelly.
Sure. Thanks, Friedel. My name's Sean Gully. I'm a co-founder here at Supernational, where we focus on hardware and software acceleration of computationally intensive algorithms. And of late, our primary focus has been around cryptography operations in the blockchain ecosystem. And prior to that, I was at Intel for about 20 years as a principal engineer, where I co-invented some of these CPU features that we'll talk about today.
Excellent. Thanks, Sean. Yeah, my name's Kelly Olson. I'm on the product team here at Supernational. And as Sean mentioned, we're focusing on accelerating verifiable and confidential computing. So back to you, Dig.
Thank you. Yeah, as I mentioned, I've been with Protocol Labs for a while now, over 4 years, and I've been focusing on the proofs implementation, and so got to work with Sean and Kelly on this. So we're going to look at 3 things today that we've worked on, as the title hints at: sealing, signatures, and SNARKs. And so let's get it started. So the first the biggest thing that probably everybody who has run a miner so far knows that there's a process called sealing, which is the first step in proof of replication. And you've likely also heard it maybe under the code name called pre-commit 1. And it is the slow, but very crucially slow part when you onboard new sectors. Sealing is designed to be very computationally intensive. That is what it makes it secure. But we end up, of course, not wanting that everyone has to pay a high cost, but only as much cost as we really absolutely need to achieve our security, which is why it's crucial that the implementations that are out there are as fast as we can make them. Now, the other part where it's really good if these implementations are faster is that the difference then between the between the honest and the malicious miners becomes less, because if all the honest miners already know the really good code and have it running, then there's simply less room for malicious miners to improve on, and as such making the network more secure. We also really want everybody to be able to mine as easily as possible. So we really want this process to be take as little resources as possible. But it, of course, unfortunately, still takes a lot of resources. But we've done a lot of work to reduce that. And Sean is going to tell you a little bit about what we've achieved there.
Thanks. Yeah, so here you guys can see on the left-hand side a picture of what's called a stacked depth robust graph. And this is from a paper by the great Ben Frisch at Stanford from a couple of years ago. That was the foundation for what's in Filecoin today. And you'll see these nodes, and each node is represented by a 32-byte SHA-256 digest. And you'll see the red lines are the edges that represent base parents. And this is all intra-layer. And then you'll see these blue edges below. Those blue edges, they are interlayer, and they represent what's called expander parents. And the idea here is that it's a very serial process, as Dig said, where you've got a node that you compute, then you've got the next node, and it relies on the previous node or the previous layer's nodes. And so what you'll do is you'll concatenate the value of those nodes that the edges connect to into a buffer, and then you'll hash it. So the key point here being that the theoretical limit to this graph, when all of the edges are kind of randomized and pointing to previous nodes, then you'll have whatever your hashing compute can handle that should be what your theoretical limit is. So when we looked at what can we do with sealing as it is, we looked in two places. One was, all right, what's that theoretical limit for the hashing? And then two, where are some of these bottlenecks? And it turns out the bottlenecks mostly are in the memory reads. So what we did in terms of the process is, most of the miners now, when you generate the graph, you'll only do it once, and then you'll cache it on your machine. So whether you're doing a 32 gig or 64 gig sectors, you'll cache that graph for later use. So if you're sealing a whole bunch of sectors, you don't have to repeat that process. So what we do is we pull that cached graph into memory, we pin it in there. You got to lock it in there so it doesn't get swapped out. So that graph is always fresh in memory. Then when we look at the buffers, we kind of map this current layer, and then we have another buffer for the previous layer. And so those are our three kind of working memory spaces to deal with. And so we put some constructs in to make those efficient. And then the next piece that we looked at was a sort of a threading. So we create one thread that's doing all of the hashing, and then we create, in this case, we use two threads for prefetching all of this previous node data. So in this producer consumer model, we create two threads that go off and run and do the prefetching based off of what's in that parent node cache. And then we have the other node that's pulling them off of a ring buffer that's shared between them and actually hashing them. So this whole process, we have another process in there that tracks, hey, what if I was prefetching a node and it was too close, so the base pair was too close, we track that, and then the hashing thread can pull that in. So we found that to be like, all right, two threads with some tuning of some parameters was sufficient enough to read ahead back, pulling out of memory or even off of disk into the localized cache. Another thing we do in this case is we also pin the process to a certain, say, complex. So in this case, we're using the SHA extensions that are in mostly the Ryzen's or AMD cores. So AMD is set up in a complex where you'll have 4 cores in a complex with a shared cache. And what we do is we pin the process to sit in that context. So you'll have maybe your hashing thread, and then you've got your prefetching thread, another prefetching thread, and they're all running tightly in this complex that all have a shared cache. So everything's really hot. And so really it all comes down to how fast can I hash, assuming all of the data is available. So we can just turn the page a little bit, and then we can see just some of the results that we got here. So we started off just using, if you kids could use like Lotus Bench and things like that to see where it was before. And a lot of people were reporting in this 4-hour-ish range. And by just doing a couple of these tricks, well, we brought it down to around 2 hours. And if you presume that the graph is entirely serial and there is no way to hash another node before you completely hash the previous node, then we are close to that sort of theoretical limit. In general, AMD can hash at 2 cycles per byte. So we could take how many bytes are we hashing in the buffer. We could figure out how many cycles it takes based off of frequency, say, about 4 or something gigahertz, perhaps. That 2-hour range is pretty close to about as fast as you should be able to seal a graph that's entirely serial. So
one thing I may add here that just may be relevant to the miners in the audience is, the AMD processors today do have this special instruction set that makes hashing faster. They have sort of a custom accelerator within the CPU. That accelerator is going to be expanding out into other both Intel and also ARM processors. But just one thing to sort of keep in mind is if you're looking to do this sealing as quickly as possible, at least today you're going to get probably the faster times using the AMD processors because of this specific accelerator for the hashing.
Yep.
Also a note, we do have experimental ARM support, and I believe technically we actually do call the current ARM instructions in most of the code. So I believe some people already reported that they are also doing this hashing on ARM with the sped up instructions if you have an actual ARM64 processor supporting those. If folks out there are running this and are seeing times, will be really interesting because we haven't done any larger tests on ARM processors. So any info that you can send our way would be appreciated. All right. So pretty good, right? 2x, that's pretty good. Let's see if we can do better. So signatures. Signatures, most blockchains, well, I'm saying most, I assume all blockchains use signatures for signing their messages or transactions, depending on the lingo. Filecoin additionally uses signatures to also in its consensus process. For sending messages, we have two options currently available, and one of them is BLS signatures. The other is the classic cyclic key. BLS signatures are have the big bonus for us that they allow aggregation. And so if you look at the block production in Filecoin, all messages that have been signed with a BLS signature, they get aggregated by the block producer to a single signature. And so if you verify the signatures for a block, you only need to verify the single aggregated signature. But that means you have to verify an aggregated signature. And so this is one of the verification methods that gets called quite heavily. The other part is we use it in the VRF to generate the election ticket. It gets signed. There's a signature based on the private key of the miner that is mining the block. And so any block validation also has to verify that signature when doing the block verification. And so you can see that every block that you need to sync and produce heavily uses these signatures. And so let's take a look how fast we have made and been able to improve on these signatures.
Great, yeah, thanks, Sig. So when we look at signatures, just in general from the BLS perspective, there were a handful of libraries that existed. Some were somewhat experimental, some were kind of driven by researchers when they were getting this off the ground. And there's a couple that were pretty good performance to begin with. But when we took a bigger look at where the problems were, we thought, hey, I think we could do a little bit better. And since this is new, this is emerging just for us, we thought, hey, this is great. Like Filecoin's using this. This has been being pushed by other blockchains as well. So, hey, we should really do a pretty nice library for this. So this is great because this is Filecoin is the first production blockchain that we've put this library into, and we created what's called Blast. And this Blast library is kind of comprised of a few different areas. One, we looked at some algorithmic approaches, and these are some of the more classical approaches to field and curve operations, like just using Montgomery multiplication, things like that. How do you represent points? Some of the endomorphisms and batch efficiencies are additional techniques that you could be used when you're dealing with a lot of different points. And in this particular case, for Filecoin, as Dig mentioned, these aggregated signatures and aggregate verification of a signature is kind of where we were starting to deal with. There's a whole bunch of points here that we're going to have to deal with, because at the end of the day, a signature just boils down to a point on the curve. So we were focusing on algorithms of that space. We also focused a lot on the assembly. So given our background, most of our experience came from assembly coding on CPUs, whether that's x86 or ARM. And one of the first things we saw when we looked at a Rust, which is what the pure sort of native Rust, which Filecoin was using before, we were able to get a 3x performance improvement just by hand tuning the code. This wasn't compiled, but it was more assembly base that was using instructions like mulxadd, cxadd-ox for parallel carry chain and things like that in the very intensive modular arithmetic. And then the last piece, which actually drove a huge performance improvement. So as you're saying, like, hey, I am a miner, I'm generating a block, I have a whole bunch of different signatures that I need to aggregate. When you look at the actual operation underneath that, that can be parallelized heavily. So I could take a huge chunk of signatures, I could break them up into buckets, I could feed them to a variety of threads. And as we talked about earlier, if you're talking about using an AMD processor, as we know, those processors now come heavily loaded with a lot of cores. And so we started to take heavy advantage of parallelization, and it was on a very fine grain using lightweight threads. So we saw that even in Rust. We played around with like the built-in libraries with Rust and decided to create a different thread pool associated with our code so that we could maximize the performance, especially over the long run. So you could see on the next slide where we ended up getting as a result. So the x-axis is the batch size. So consider this, a single value would be a single signature, and then so on the left is aggregating signatures. So if you're a miner producing a block, now you've aggregated, say, all the way on the right hand side would be, say, 1,000 signatures, and then on the right hand graph, this is signature verification. So I've got an aggregate signature, and as part of that aggregate signature, you need a whole list of public keys and a whole list of messages associated with it. So it also could be heavily parallelized. And so what we see is we're tapping out in this 5 to 8x performance improvement range. So we were seeing that potentially 3x off the bat with some of the assembly optimizations that were made and some of the algorithmic optimizations. And then by adding the threading, we started to get that much bigger boost. So the whole key point here is that we're trying to alleviate bottlenecks in the system, so it allows you to decrease block times. It gives you a little bit more room to transfer things over the network, which could be a little bit haphazard. It can allow for more things in a specific block. So all told, it really, by expanding it to these bigger numbers, now we can really scale Filecoin much greater. So I think we're pretty happy with the result.
Nice.
SNARKs. Yeah.
All right. Well, that's pretty good. 5 to 8x. All right. Anybody think we can do better? Anybody want to do better than that? All right. Let's take a look at our third problem, SNARKs, or short for ZK SNARKs. So ZK SNARKs have been around for a while. Well, in crypto terms, they haven't been around for a while, but in blockchain terms, I think they have been around for a while now. And they are starting to get more and more adoption by different systems in order to improve what can be done in terms of computations off-chain, but verified on-chain. Filecoin very early on decided to use this to allow the proofs of storage that we need to do to be verified by all participants on-chain. And so we currently use this for the PORAP in order to make the commitment to the storage and to prove the correctness of the aforementioned seal. We generate currently 10 SNARKs. Well, every miner generates 10 SNARKs when they onboard a sector of 32 gigabytes. And then for post, both winning and window post generate a SNARK that gets posted on chain for every such post. So you can see that we generate quite a lot of SNARKs, but especially there's a lot of need to verify these SNARKs, as everybody needs to verify the blocks that contain these SNARKs to get posted on chain. So we've looked heavily into SNARK verification as such, and so Sean will tell you a little bit about what we achieved there.
Thanks, Eddie. So, as Dave just mentioned, the SNARK verification can be a pretty big bottleneck. And I guess, today already we're seeing thousands of SNARKs being generated by Filecoin a day. So anything we can do to speed this up, once again, helps impact scalability and helps improve validator performance. So when we look at it, there's as you mentioned, there were 3 different types of proofs that would need to be verified. So that winning, the seal, and the window post. And realistically, where the bottleneck becomes is in this multi-scalar multiplication operation. And each one of the proofs has a different number of points that need to be multiplied and added together. And you can see winning and seal are relatively small, but window is much larger. And window is the thing that you're constantly being challenged on. So this is it's a pretty common SNARK to be getting, and it's not just a one-time thing. This will be happening over and over and over again through the life of the storage. So it was a big area of focus for us. And so we looked at, again, that 3 sort of areas. We're looking at the algorithm, we're looking at assembly code, and we're looking at multi-threading. So from an algorithmic perspective, the interesting thing about the SNARKs was we had some interesting opportunities here for pre-computation. So there's a verification key that was generated along with the SRS, the structured reference string, as part of the parameter generation, the trusted setup. So these values are fixed for all time, and we could pre-compute some things. So there's some Greeks. You can see that the formula is is there. It's a little convoluted, but you can see we could do some pre-computation on some of those Greeks, and then we could also pre-compute on some of those points in that middle sigma function right there. And we ended up using this fixed window, this 8-bit fixed window multi-scalar multiplication operation, and that dramatically sped up the performance. And another thing is these pairings. So there's not just the multi-scalar, there's 3 pairing operations. We combined the 3 pairing operations into one, and we also would do those operations in parallel with the exponentials, the multi-scalar multiplication. So that parallelism starts coming in that multi-threading. So we talked about the Groth 16 is the proof system that they use, but we use the pairing and the exponentiation together in parallel. But there's another added feature that we had that helped significantly improve performance, and that was deserialization of these proofs. So as they get sent over the network, they come in, we need to deserialize them. And then as part of the validation responsibility, you're supposed to check, hey, are these valid points in the group, the elliptic curve group? So that's another expensive operation. We're able to parallelize that. So between these sort of 3-4 different buckets here, we were able to shrink it and dig on the next slide. You can see the performance that we were able to get across the 3. So, on the big one, on the window, which is happening every day, we've got the 12x performance improvement. So that made something that was, a scalability potential concern, and we shrunk it down a lot. So this is great. So this means, there's an opportunity for more challenges, or there's an opportunity just to validate a lot more storage and challenge a whole lot more storage on the network. And similarly, we got 10x and 8x respectively for winning and seal. So again, this is all lightening the load on validators. So we were also extremely happy with these performance improvements.
Yeah, I think one thing to add is, this work and the use of SNARKs is really groundbreaking here for Filecoin. So as Sean mentioned, I think, we're seeing at least 8,000 or 9,000 SNARKs being processed today by the network, which I think is, unprecedented on mainnet systems today, right? So this is a 1 SNARK every 10 seconds or something like that. And, even on some of the maybe more established blockchains, we're not seeing this sort of use of advanced cryptography. So it's really groundbreaking work, and I think this optimization work is going to be more important as SNARKs are more widely deployed by not only Filecoin but also other blockchain networks.
Yeah, one small note to these things and when they will get deployed. As Nicola mentioned earlier in the chat, the sealing improvements are currently in Lotus, and at least most of them, and there's a link to instructions on how you can enable them. They're currently still marked as experimental until we have further wider testing. The SNARK verification and the SNARK verification is coming soon. It is currently partial. You can currently also enable it. There's a use fill blast flag that I believe we have some documentation. We'll post something later in Slack and the fill proofs channel for details. And the BLS improvements are actually already deployed by default currently in Lotus. They are only in Lotus deployed as far as I know. I don't know about Fuhuan and Forest on the state there, but I know that they are deployed in Lotus currently. Yeah. Sweet. All right, so the future. So there's certainly a future here. This is not the end, this is the beginning, now that we have mainnet anyway. And in performance optimization, certainly there's still a lot to be done. This is also a call to the community. We really want your help and any ideas, how crazy they might be. Some of the ideas that we had were certainly crazy, but they did work out, so that's nice. Send them over, make PRs, let us know what ideas you have to make these things faster. It just benefits the whole community if the default implementations get better and better, and people can learn from this code. All the code that we've discussed so far is already open. It's just not necessarily integrated already in the chains. Some of the topics we hope to be looking into, or I already started looking into for the next, are snark proving. As I mentioned earlier, snark proving is still pretty heavy for all miners. So making that better and faster is definitely going to help the network. Syncing is still not as fast as we would like it to be. So improving that in all areas is going to be a focus. And then BDFs are the next level. We're still looking into BDFs, and especially Supranational has been working on them for quite a while. And hopefully at one point we will have a VDF that can integrate into Filecoin. So definitely stay tuned there. Yeah, thank you, everyone. Kelly, Sean, if you want to say some last words.
I think that's great. You know, certainly feel free to reach out to any of us here on the panel today if you have any questions. You know, always looking to you know, add value or expertise if there are questions that you have for your projects or your deployments.
Yeah, and I just want to thank the Protocol Labs and Filecoin guys and the whole team. I mean, it's been great. I mean, you guys have been super receptive to just improving. And so you guys every single day are doing your best to improve the protocol, improve the network, improve the code base solid. So, I mean, it's a super solid project with a great team. So we're ecstatic to be a part of it.
Yeah, I want to extend that thanks to Supranational. They have been amazing partners, and they have been teaching us, at least me, and I know some of my teammates, day in and day out, and how computers work and how to make them do what you want a little bit faster. So thanks so much.